I just want to say welcome back to the podcast, where this podcast will illuminate the hidden forces that govern our world. So let's start off with segment 1, which is Coulomb's law. So our story begins with Coulomb's law, a fundamental principle that describes the force between 2-point charges. So imagine two charges suspended in space, exerting a force on each other. So this force is proportional to the product of charges and inversely proportional to the square distance between them. It's fascinating to think that this law governs interactions from the atomic scale to the cosmic phenomena. So have you ever wondered how charged particles interact in the vast vacuum of space, or even in the air around us? So, answer this question. Consider how electrostatic force compares with gravitational force, especially between subatomic particles. Why might one dominate over the other in different contexts? This marks segment 2, which is the electric field strength. So, with Coulomb's law in mind, let's explore electric field strength. So, electric fields permeate space essentially emanating from charges, shaping the paths of other charges with them. Represented by field lines, these charges direct charged particles in uniform and radial arrangements. But what defines the strength of this invisible force field? So simply, it's the force experienced by a unit charge placed within it. So from the sparking gap of a Van de Graaff generator to the delicate equilibrium of Earth's atmosphere, electric fields shape the world around us. Ever ponder the trajectory of a charged particle zipping through these fields? So, answer this. So, visualize a charged particle entering a uniform electric field. How does its path exactly change, and what factors influence this trajectory? This marks section 3, which is the electric potential and potential difference. So as we journey deeper, we encounter electric potential, which is a concept that measures the potential energy per charge at a point in an electric field. It's a bit like measuring the gravitational potential energy at different heights, but for charges in electric fields. This potential is zero at infinity, growing more negative or positive as you move away from the charges. And what about when we move a charge within this field? Well, the work done is tied directly to the potential difference encountered. This brings us to equipotential surfaces. They're invisible, yet powerful, as no work is done when you move a charge along them. So how does this shape our understanding of energy in electric fields? So pause for a second and imagine moving a charge in various paths around an electric field. Why is the concept of equipotential surfaces so revolutionary in simplifying our calculations? So, to conclude, from the push and pull of Coulomb's law to the guiding lines of electric fields and the energetic landscapes of electric potential, today's episode has zapped through the core of electric fields. These principles illuminate not just our understanding of the physical world, but also power the technological innovations that drive our society forward. So next time you flick a switch or witness a lightning bolt, remember the intricate dance of forces and fields at play. Now I just want to add the use and the actual equations used in this topic. So at the heart of Coulomb's law is a beautifully simple equation, which is F equals 1 over 4 pi epsilon naught multiplied by Q1 times Q2 over R squared. Now this is also written quite usually as F equals K Q1 Q2 over R squared, where K is equal to 1 over 4 pi epsilon naught. So here F is the force between two charges, which is Q1 and Q2, separated by distance r. Now, of course, epsilon naught representing the permittivity of free space. This equation tells us that the electrostatic force decreases with the square of the distance, a concept that might remind you of the gravity law, but with a unique twist for charged particles. Now, this is segment 2, which is the electric field strength. So as we dive into electric field strength, we encounter the equation which is E equals F over Q, where E represents the electric field strength, F is the force on a charge, and Q is the charge itself. This leads us to another expression for electric field strength in the uniform field, which is E equals V over D, connecting the voltage across the plates, the distance between them, and calculating the electric field strength from them. So it's fascinating how these equations reveal the invisible forces at play around us. So now, when we talk about electric potential, we're really discussing energy per charge. The equation V equals KQ over R shows us the potential, or voltage, at a distance r from a charge Q, with epsilon naught again denoting the permittivity of free space. Moreover, the relationship between electric field strength and potential difference is elegantly captured by E equals delta V over delta R, where delta V is the change in potential over the distance r, or delta R. These equations are not just symbols, they are the language of the universe, allowing us to quantify and understand the unseen forces that govern the behaviour of charged particles. Thank you for listening to the podcast. Have a great day.